Hey guys, today we're going to be doing one-way reactions. Our syllabus outcome is to analyze examples of non-equilibrium systems in terms of the effect of entropy and enthalpy, for example, combustion reactions and photosynthesis. So before we actually go into too much, we're going to revise some topics from Module 4. In particular, we're going to look at collision theory, enthalpy, entropy, and Gibbs free energy. So these are the things that we studied in Module 4. If you need a refresher on that, go back to Module 4, have a look at those in a bit more detail. We'll just go over them a little quickly today so we can get through everything. First thing is collision theory. Now, collision theory states that for a reaction to occur, molecules need to collide with enough energy and in the correct orientation. If we have a look at the diagram there, it's a reaction of carbon monoxide with oxygen to form carbon dioxide and an oxygen-free radical. Basically, if the reaction occurs oxygen to oxygen, like in that top reaction, it's not actually going to occur because CO2 is a carbon in the middle, oxygen's on the outside. So that's not going to be conducive to a reaction occurring. So while that collision, it's probably collided with enough energy, it's not in the right orientation. If you look at the bottom one, if the carbon monoxide collides with the oxygen with the carbon side, then we're going to get a successful reaction. We're actually going to get carbon dioxide formed. Now, the thing with collision theory is reactions favor the collisions that occur more easily. So if there's more successful collisions, faster reaction rate, more reaction occurs, basically. Okay, there's lots of different things that can increase your reaction rate. So that increases the collisions. So if you increase the concentration, you increase the collisions. If you increase the temperature, you're increasing the energy, increasing collisions or successful collisions. And there's a few other things that you can go back and revise. Another thing we have to look at is reaction profiles. So during a reaction, we deal with a lot of energy stuff. Okay, reactants have energy, products have energy, and the reaction profile shows the amount of chemical potential energy contained within the molecules during the reaction. So remember, total energy of a system is potential energy plus kinetic energy. Um, for reaction profiles, we're just looking at the potential energy, so the stored energy, and we're just looking at this energy that's stored within the chemical bonds themselves. Here's an example. This is a reaction profile where the reactants start about middle of the potential energy scale. It goes up to an activated complex. That's what we call when um, the molecules collide, and before any bonds are broken again, it's this really high energy sort of thing. It's an intermediate, basically. Then bonds break and we go to the products. So in this case, our products are lower potential energy than our reactants, but our activated complex is much higher energy, and things don't like to be high energy. Okay, so it's going to slide down to that products. Activation energy, so that thing where we're talking about the transition state, the activated complex, that's what we call the activation energy. So for a reaction to occur, we need to get over that energy hump, and it's the extra energy required for a reacting molecule to get converted into the products. I said before, collision theory states enough energy in the correct orientation. That enough energy is the activation energy. The extra energy comes from the collision, so we basically get the kinetic energy of the colliding molecules. So remember, they're always moving around, bouncing around. They collide into each other. That gets transformed into their chemical potential. So bonds are formed, makes this high energy activation complex, and then it moves onto the products. Okay. In terms of reaction rates, lower activation energy is better for our reaction rate. So faster reactions occur with lower activation energy. So um, something with a high activation energy, not going to occur naturally or not going to occur quickly. Something with a low activation energy will occur quite quickly. And that again comes from successful collisions. If you need a really high energy collision, then it's not going to occur as often, um, and so it won't be as quick in the forward direction. Looking at endo and exothermic reactions. So an exothermic one is where our products have less potential energy than our reactants. So if you remember from module 4, our delta H is negative. Basically, it's where all this chemical potential energy that's stored in the reactants is lost. Where is that energy lost to? It's lost to kinetic energy in the form of heat. So that's why exothermic reactions get hot, because there's all this stored chemical energy that has to go somewhere. Where does it go? It goes into heat. It heats up the water or whatever you're doing the reaction in. Okay, so it gives it to the surroundings. Endothermic reactions are the opposite. So we end up with products that have a higher potential energy than our reactants. Now, to increase potential energy, that energy's got to come from somewhere. Remember, law of conservation of energy. Energy can neither be created nor destroyed, it just transforms. So the energy that goes into the chemical potential that increases it comes from the surroundings. That's why it gets cold. So endothermic reactions get cold. And again, that's coming from transforming the kinetic energy of those particles into chemical potential energy. Now, enthalpy. Enthalpy is the specific name we give for that difference in chemical potential energy between the reactants and the products. We measure it in joules, though it's commonly quoted in kilojoules. And that's just because of the scale that we do it on. Molar enthalpy, on the other hand, is the change in enthalpy per mole of reaction. It's measured in joules per mole, commonly quoted in kilojoules per mole. And again, this is a standardization. So if we do it per mole, we can compare the combustion of 1 mole of ethane to the combustion of 1 mole of propane, for instance. And it helps us standardize it. We typically use delta H naught for this. So it's just like a little degree symbol after the delta H. And we call that molar enthalpy. And that's just delta H on N. So that's module 4 stuff again. Going back to have a look if you need it. Entropy. Now, entropy is a bit of a weird one. The best way to describe to you guys, it's the measure of disorder or freedom within a system. Basically, the more possible states that a molecule or a set of molecules can take, the higher the entropy. If we look at our reaction equation, the side that produces more moles, that has more entropy. So for example, if we take something like octane and burn it, it's going to produce like 8 molecules of carbon dioxide and like 9 molecules of water or something like that. And so we're going from 1 to many. So that's a massive increase in entropy. The other thing as well is higher temperature gives more entropy. So if something increases in temperature, it's increasing in entropy. That should say gas. Gas has a higher entropy than liquid, which has a higher entropy than solid. Because again, a solid's nice, tight, compact, it's locked in, it doesn't move much. Liquids move over a little bit, they've got a bit more freedom, but they still take the shape of their container. Okay, they're still like they just sit there. Whereas gases, they can just go whiz around everywhere. They can do whatever they want. Okay, they can bounce off all the walls everywhere. They have a much higher freedom than anything in a liquid or a solid. Now, Gibbs free energy. Gibbs free energy is a thermodynamic potential energy of a chemical system. This is a bit of a weird one. We've learnt of enthalpy and we've compared that to H. We've compared that to Q. And we've kind of gone, it's the same thing, but it's not really. The amount of energy that we can use to heat our surroundings is our Gibbs free energy. Okay. And it's basically our enthalpy minus the energy lost to entropy. Okay. It can be higher or lower than delta H depending on our entropy values. But generally it's not going to change all that much. Sorry, excuse me. The important part of this, though, is that the change in Gibbs free energy dictates whether a reaction will occur spontaneously or not. Typically, a negative delta G is what we call a spontaneous reaction, something that will occur by itself. We don't need to put energy into it. We don't need to change the temperature or anything like that. Our Gibbs free energy, it's given by the equation delta G equals delta H minus T delta S. So that's our Gibbs free energy is given by our enthalpy, take away our temperature times our entropy. Okay, and these are all the standardized ones. So we're looking at molar enthalpy, we're looking at molar entropy, and we get molar Gibbs free energy. So they're measured in joules per mole. In the last lesson, we observed 4 reactions. Now they were cobalt chloride, the hydration and dehydration of that was the red-blue one. We had burning magnesium, so we stuck some magnesium in a flame and it went off. It likes to glow nice and bright, and it did not reverse. Like whatever we did, whatever we tried to do, nothing could reverse that reaction. We added thiocyanate ions to iron ions. We had a nice blood red compound that was formed, which is iron thiocyanate. Get used to that one, it pops up a few more times in future lessons. We reversed that successfully by getting rid of the iron from the solution, precipitating it out, and then that blood red disappeared. And the last one is we burnt some steel wool. And again, just like the magnesium, it glowed a bit, but whatever we did, we couldn't get the iron back. Now, thinking of those, describe those 2 reactions that were not reversible. What do you notice about them? Me personally, I noticed that they produced a lot of light, produced a lot of heat. We needed a fair bit of activation energy to get them started. Okay. So burning steel wool, it occurred according to the following reaction. 4 iron plus 3 oxygen gives us 2 iron oxides. It was exothermic, it had that orange-red glow to it. As it was burning, it's quite spontaneous. And if we look at that equation, there was a decrease in entropy. So we went from 7 molecules on the reactant side to 2 on the product side. Same with burning magnesium. We lit it up, it glowed white hot. The 2 magnesium atoms reacted with an oxygen atom to form magnesium oxide. Super exothermic, it burns at like over 1,000 degrees. It burns really white hot. So big delta H, a negative delta H at that. There was also a decrease in entropy. So if we look at it, we go from 3 molecules to 2 molecules. We go from a solid and a gas to just a solid. Okay, big decreases in entropy. Now let's have a look at at 2 other reactions, combustion and photosynthesis. So combustion, we know what combustion is. It's when we light something on fire, basically. Here I've got the combustion of ethanol, so just straight alcohol, 2C2H6O plus 7 oxygens give us 4 carbon dioxide and 6 waters. Now, it's an exothermic reaction, big change, big negative delta H. There's a slight decrease in entropy, so even though more moles are produced, we start with more gas. So we have 7 gas, 2 liquid. We end up with 4 gas and 6 liquid. Okay, slight decrease in entropy. So look at photosynthesis. So this is the reaction that occurs in plants. We have 6 carbon dioxides plus 6 waters, gives us 1 molecule of sugar and 6 oxygen molecules. Now this reaction, does it ever occur spontaneously? Well, the answer is no. Because for a plant to photosynthesize, we firstly need all the like chloroplasts and the chlorophyll and all those other fancy molecules that are needed. We also need sunlight, lots of energy from that to start our electron chain transfers. So for that to occur, it's not spontaneous. It's highly endothermic and the entropy decreases. Okay. But let's look at the reverse of that. Cellular respiration, which is the ones that we use in our body. We take in sugar, we take in oxygen, we expel carbon dioxide and water. It's basically at a reaction level, the reverse of photosynthesis. So the signs of all the thermodynamic data are reversed. It's a highly exothermic reaction, entropy increases. Now, What do you think is the reason that all of these reactions are one way? In particular, look at cellular respiration, look at combustion, look at burning of magnesium, burning of iron. All of them go one way. Why is that? Now, I'm going to leave you on that. I'm not going to tell you the reason for it, but I'm going to leave you on that note. Have a think about it, see if you can figure it out. Okay.